Hi everyone, this video is going to be on sensor data in mobile robotics. So the first question we need to address when talking about sensor data is, what is a sensor? Well, a fairly basic definition is that a sensor is a device that captures and quantifies a physical phenomenon. So we have something physical here in our world, be it light or sound waves or something else. A sensor can capture something about this phenomenon and transform it into some kind of usable representation. Typically, it's a digital signal. For everything that we'll talk about in this course, it transforms it into a digital signal. This is nice because then it can be easily represented with a computer. And once we get these signals, we can use them to reason about a robot's environment or even about the robot's internal state. There are a few different ways to differentiate types of sensors. One of them is active versus passive sensors. Active sensors are ones that emit energy into the environment and they measure something based on the response. So laser-based sensors are a great example. They emit some laser and they wait for that laser to hit something and get back to the starting point, and then they measure the time of flight. Passive sensors are just not active, so they do not emit any energy into the environment. Compasses, for instance, just react to magnetic fields, and cameras just accept in light. Another pair of classifications could be proprioceptive versus exteroceptive. Proprioceptive sensors are used to measure the internal state of the robot, so something like a gyroscope or a force torque sensor. Exteroceptive sensors generate information about the external environment, so a laser or a camera. The reason that we're interested in sensing at all is for the purpose of perception. I've copied the perception pipeline example from the Handbook of Robotics here, and you'll notice there are many steps, but the input is always some raw sensor data, be it from a laser sensor or a camera sensor or just some other kind of sensor that's going to give us data. In this class, we're not going to be concerned with how the sensors actually work. Instead, we're going to be concerned with how they enable us to do perception and then how we can use perception to do larger robotics tasks. So in this video, we're going to look at what kind of data sensors can give us, what are the pros and cons of different types of sensor data, and then in subsequent weeks, we're going to look at how to extract features out of that data and then how to use that to enable a robot to make sense of where it is in an environment. We're only going to look at 3 different types of sensors in this video because these are the 3 most common sensors in mobile robotics. They are in IMU, cameras, and laser-based sensors. IMU stands for Inertial Measurement Unit, and they're a combination of 3 individual sensors. An IMU outputs angular acceleration, so as some system rotates, this sensor can detect the acceleration along each axis, and then we can simply integrate that data to obtain the orientation of the system. IMUs are incredibly common sensors because there are so many applications where you want to know the orientation of some system. You'll find them in pretty much all smartphones, even dating back to the first iPhone. They're used in pretty much all mobile robotics because they're very accurate at giving us the robot's direction, and they're even used to help guide heavy aircraft. Cameras, of course, take in light and output an image. Digital cameras take it a step further and they store the image in a file. And the file is a 2D array of numeric values that represent the color for each pixel. With these large arrays, we can detect all kinds of geometrically interesting points in the image. We can also apply machine learning techniques to learn various high-level patterns in the data, like detecting faces. The resolution of a camera matters a lot. More pixels typically makes it easier to understand an image, but it comes at the price of a lot more computation to apply computer vision techniques. Similarly, color can make some computer vision tasks easier, but at the cost of more computation, so we typically want to know if a camera can output grayscale or color images. A laser rangefinder sends out lasers into an environment, and then eventually that laser will hit something in the environment and bounce back to the sensor, and the sensor measures the time that it takes for the laser to return. It rotates the direction that it sends out the sensors, and once it completes a full scan, you get an array of distance values, where each value is the distance that the laser reached at that specific angle that, of course, is relative to the sensor. If a sensor gets sent out and it doesn't actually hit anything in the environment, maybe there's a gap in the wall or something, then rather than a numeric value, you may get a null value or some kind of negative value to indicate that it never actually hit anything at that angle. There are a few important features that we care about for these sensors. The resolution is the angle between the measurements. So in other words, how many values does it actually return in a single scan? We also care about how quickly it can do the scans and how far away it can send out the lasers and get information about the environment. And we care about the field of view for the scans as well. RGB cameras are cameras that return both the light information about the environment and the depth information about the environment. They're typically made up of a few sensors all packed together in one. So here's an example of one down here where we have a normal camera, just an RGB camera, but we also have a depth camera that detects the depth in the environment, and then we have an infrared sensor which supports these other two. These sensors return something called a point cloud, which is like an image, but each pixel has an associated depth value. So you get the light information as if you took a normal 2D image of the environment, but you're able to use the depth of each pixel to make sense of the environment as a volume rather than as a flat image. The advantage of these over 2D cameras and simple laser rangefinders are that you get both types of data. So these are great sensors if your environment is small and your application might require some manipulation of objects. But if your environment is large, then these might not be a great fit, because the disadvantages are that typically the camera part is lower resolution than non-RGBD cameras, and they have a smaller field of view and a smaller max depth than laser rangefinders. So let's revisit laser sensors because we need to broaden that discussion to include LiDAR. LiDAR is the process of sending out light to get range data. Even though that's how we described the laser rangefinder before, LiDAR is the technical term for that process. What we saw before was a laser being sent out at different angles, but it was only being rotated about one axis, and it had a pretty limited field of view. Some LiDAR sensors can rotate the light on multiple axes in order to produce a point cloud of the environment. We typically call these LiDAR sensors. So when you hear someone say LiDAR sensor, they're very likely talking about a range-finding sensor that uses light and whose field of view is 360 degrees, so full circle around, and the max depth is very large, like usually hundreds of meters. So in this video, we talked about how sensors convert physical phenomena into some representation that we can use, and usually that's a digital signal. Sensing and perception in robotics is a pretty large pipeline, and it involves many different fields, computer vision, machine learning. We're not going to be able to talk about how all these fields come into play in this class, but as you continue in the curriculum here, you'll probably take some classes that touch on all of these. The most common sensors in robotics are LiDARs, cameras, and IMUs. And in this class, we're going to use a 2D LiDAR to sense the robot's environment. So because it's 2D, that means the laser is only being rotated about one axis. So it's returning that one single scan of the environment and not a full point cloud.